In the uncharted darkness beyond Neptune, where the known solar system fades into the cold embrace of interstellar space, a planet was discovered that broke every rule of planetary science. A colossal and silent entity designated Z9979, floating like a riddle wrapped in the very laws of physics themselves. Its surface unnaturally smooth in some regions and punctuated by symmetrical craters in others, leading astronomers and physicists to question whether they were truly looking at a natural object or something built, perhaps long ago, by intelligences far beyond our comprehension. And it was not just its eerie, artificial appearance that stirred unease among scientists, but the fact that Z9979 did not behave like any celestial body we've ever observed, for its orbit wasn't governed purely by the gravity of the Sun or nearby stellar objects, but instead seemed to subtly adjust in harmony with undetected forces, almost as if it were responding to ripples in the very fabric of space-time, with movements that aligned suspiciously with gravitational wave detections that should have had no effect on its position. And this orbital peculiarity gave rise to the first whispers of a more profound mystery, that perhaps Z9979 was more than just a rogue planet. It was possibly a vessel, a machine, or even a hidden observatory silently watching us from the fringes of the void. And when the James Webb Space Telescope focused on it with its powerful infrared and spectroscopic instruments, the data that returned was so strange, so alien, that it caused a quiet storm within the halls of astrophysical research, showing that the planet absorbed nearly all light that touched it with an albedo close to zero, making it appear darker than any known celestial object. Even black holes, when viewed indirectly through their gravitational lensing effects, appear more luminous than this. And it was then that the real surprise came, when radar pulses beamed toward Z9979 returned echo patterns inconsistent with a solid or even porous rocky body, but instead revealed a series of voids and cavities beneath its surface, vast hollow regions laid out in irregular grid-like geometry, some echoing back metallic reverberations, others absorbing the pulses entirely as if coated with materials that could dampen electromagnetic interference. And while mainstream science remained skeptical, certain theoretical physicists began circulating an old hypothesis rebranded for a new age, the hollow planet theory, not as a pseudo-scientific oddity, but as a speculative framework to interpret what appeared to be artificial megastructures embedded within planetary shells, supported by comparisons to Dyson spheres or Niven rings, albeit on a much smaller scale. And although no direct visual images have pierced the crust of Z9979, the modeling suggests internal chambers spanning several kilometers, with pressure-stabilized voids potentially capable of supporting machinery or even biological systems. And then came the signal, faint and narrow, barely distinguishable from the galactic background noise, picked up by multiple arrays, including those in the Very Large Array in New Mexico, and a reactivated antenna in Arecibo that caught a repeating pattern centered around the 420 MHz hydrogen line, the universal frequency of neutral hydrogen that many believe would be the chosen channel for any interstellar communication. And the signal was strange in its simplicity. A string of prime numbers followed by the sudden introduction of the mathematical symbol for infinity, not in human ASCII code, but in a structure that suggested not just intelligence, but an understanding of math as a universal constant beyond any terrestrial culture. And what truly unnerved those who analyzed it was the fact that the signal did not remain static, it evolved. It shifted over weeks into complex harmonic sequences and recursive patterns, as though responding to its own echo, or worse, to something it had detected from Earth's direction. And skeptics claimed this could be a bizarre natural pulsar artifact or instrument feedback. But cryptographic experts at SETI and JPL quietly agreed it bore hallmarks of design transmission, which triggered a deeper level of investigation, especially after amateur astronomers using backyard radio telescopes began to report strange audio modulations when attempting to tune into the same frequency, including whispered patterns, mirrored speech samples, and audio that, when reversed, bore eerie resemblance to pre-World War II radio broadcasts from Earth, including static-laced fragments of human voice reciting numbers in German, Russian, and English. And this cascade of impossible coincidences led to more troubling theories, including that Z9000-979 might not be sending signals it could be reflecting them, selectively echoing transmissions it had recorded from Earth decades ago, and playing them back with unknown intent. And here the theories began to diverge wildly. Some proposing Z9000-979 was a passive archival station, collecting signals across time like a celestial tape recorder. Others suggesting it could be a kind of interstellar lighthouse, broadcasting beacons at specific evolutionary thresholds of nearby civilizations. And the darkest theory yet posited that it was a warning system, transmitting only when it detected technological civilizations reaching certain levels of radio output, like Earth has done since the early 20th century, thereby awakening dormant protocols programmed into its hollowed interior by ancient architects whose motives remain incomprehensible to us. And while these ideas still sit at the edges of mainstream science, they are being taken seriously enough that a classified branch of ESA and NASA have reportedly begun discussing the logistics of sending a drone-powered probe towards Z9000-979 within the next 20 years, using a combination of gravitational assists and experimental propulsion to reach it by the early 2100s. But as plans are drafted and public knowledge slowly grows, so does unease. For if the planet is what some believe it to be, relic or a remnant of a civilization so far ahead of us, we can barely perceive their intent, then perhaps we are meddling in forces we do not yet understand. For the greatest concern now is not what lies beneath the surface of Z9000-979, but the realization that its arrival in our sensors may not be coincidence, that it may have been waiting patiently for the right moment to become visible, hiding just beyond the limits of our detection until we were ready, not scientifically, but cognitively, to interpret its presence. And now that it knows we are watching, the question echoes across observatories and institutions alike, whispered late at night by those who dare entertain its implications. What happens next, now that it has our attention? In the earliest days of human consciousness, long before telescopes, rockets, or even the written word, our ancestors looked up at the night sky and wondered what lay beyond the veil of stars. Ancient civilizations crafted myths and stories to explain the heavens, imagining gods, monsters, and divine chariots moving across the firmament. And though these early interpretations were poetic rather than scientific, they marked the first step in our quest to understand the cosmos. The Babylonians tracked the motions of celestial bodies, the Egyptians aligned their pyramids with stellar constellations, and the Mayans developed intricate calendars based on astronomical cycles, all contributing to an emerging awareness that the universe operated with a kind of order. Yet it wasn't until the ancient Greeks that humanity began to approach the cosmos with a more systematic, empirical mindset. Thinkers like Pythagoras and Plato speculated on the spherical nature of the Earth, while Aristotle proposed geocentrism, the belief that Earth was the center of the universe and all other celestial objects revolved around it. This model was formalized by Claudius Ptolemy in the 12th century CE, and it would dominate Western thought for over 1,000 years, reinforced by religious and philosophical dogma. For centuries, the Ptolemaic model was unchallenged, a cosmos of perfect spheres orbiting a central Earth, stable and unchanging, until the Renaissance ignited a scientific revolution that would dismantle millennia of assumption and replace it with empirical inquiry. In the early 16th century, Nicolaus Copernicus proposed a radical idea. What if the sun, not the Earth, was at the center of the universe? His heliocentric model was not immediately accepted, but it planted the seed for future upheaval. A few decades later, Galileo Galilei, armed with a telescope of his own making, observed the moons of Jupiter, the phases of Venus, and the rough surface of the Moon, providing direct evidence that celestial bodies did not revolve around Earth and that the heavens were not immutable. His discoveries led to his infamous trial by the Inquisition, but the truth had already taken root. Johannes Kepler refined the heliocentric model with his laws of planetary motion, showing that orbits were elliptical, not circular, and that planets move faster when closer to the Sun. Then came Isaac Newton, whose Principia Mathematica unified terrestrial and celestial mechanics through his laws of motion and universal gravitation. laying the foundation for classical physics and transforming the universe from a mystical domain into a comprehensible machine governed by laws. For the next 2 centuries, Newtonian mechanics reigned supreme, enabling everything from planetary predictions to engineering marvels. But as precise as his equations were, they eventually proved insufficient to explain the more subtle intricacies of space and time. The 20th century heralded an even more profound transformation in our understanding of the universe, starting with Albert Einstein's theory of special relativity in 1905, which proposed that the laws of physics are the same for all non-accelerating observers and that the speed of light is constant, regardless of the observer's motion. Then, in 1915, Einstein introduced general relativity, a revolutionary theory of gravity in which massive objects distort the fabric of spacetime itself, replacing the Newtonian view of gravity as a force with the concept of curved geometry guiding the motion of planets and light. General relativity predicted phenomena like gravitational lensing and black holes, both of which would later be confirmed by observation. Around the same time, Edwin Hubble made a discovery that changed everything. Using the 100-inch Hooker telescope at Mount Wilson Observatory, he observed that galaxies were moving away from us, and the farther they were, the faster they receded. This implied that the universe was expanding, a realization that led to the formulation of the Big Bang theory, which posited that the universe began as an extremely hot, dense point around 13.8 billion years ago and has been expanding ever since. The Big Bang theory became the cornerstone of modern cosmology, supported by multiple lines of evidence, including the cosmic microwave background radiation discovered by Penzias and Wilson in 1965, a faint afterglow from the universe's infancy that provides a snapshot of the cosmos just 380 years after its birth. Throughout the 20th and early 21st centuries, space exploration brought an entirely new perspective to our understanding of the universe. The launch of Sputnik in 1957 by the Soviet Union marked the beginning of the space age, followed by the first human in space, Yuri Gagarin, in 1961. The Apollo missions culminated in the 1969 moon landing, giving humanity its first literal step beyond Earth and a breathtaking view of our planet suspended in the void. Robotic probes like Voyager 1 and 2 expanded our reach into the outer solar system, sending back unprecedented data and images of Jupiter, Saturn, Uranus, and Neptune, while telescopes like Hubble allowed us to peer billions of light years into the past, capturing galaxies formed shortly after the Big Bang and revealing the sheer scale and beauty of the cosmos. Milestones continued to accumulate: the discovery of thousands of exoplanets in distant star systems, the detection of gravitational waves by LIGO in 2015, confirming a key prediction of general relativity, and the construction of powerful new observatories like the James Webb Space Telescope, capable of probing the earliest light in the universe and examining the atmospheres of alien worlds for signs of life. Parallel to these discoveries was the refinement of our understanding of the universe's composition. Scientists realized that the matter we can see, stars, galaxies, planets, makes up only about 5% of the universe. The rest consists of dark matter, an invisible substance that exerts gravitational influence on galaxies and clusters, and dark energy, a mysterious force driving the accelerated expansion of the universe, first detected through supernova measurements in the late 1990s. These components remain some of the greatest puzzles in modern physics, with no confirmed direct detection of dark matter particles or a clear theoretical explanation for dark energy. All of this has led us to our current conception of the observable universe, a term that refers to the portion of the universe we can, in principle, observe from Earth, limited by the speed of light and the age of the universe. Because light takes time to travel, when we look out into space, we are also looking back in time. The observable universe stretches about 46.5 billion light-years in every direction, encompassing an estimated 2 trillion galaxies, each containing hundreds of billions of stars. Yet beyond that horizon lies a potentially infinite universe we may never see or understand. The concept of the observable universe is crucial, for it reminds us that our knowledge, while vast compared to our ancestors, is still fundamentally constrained by the laws of physics and the nature of space and time. It also hints at the possibility that other regions of the universe, perhaps with different physical constants or laws, could exist beyond our reach, and some theories, like cosmic inflation, suggest that our entire observable universe is just a tiny bubble in a much larger multiverse. The historical trajectory of humanity's understanding of the cosmos has been one of exponential growth, from mythology to mathematics, from astrology to astrophysics, and from earthbound speculation to interstellar observation. Each generation has built upon the discoveries of the last, overturning sacred assumptions and embracing ever more sophisticated and sometimes unsettling truths. We have learned that we are not at the center of the universe, that our galaxy is one among trillions, and that the fabric of reality itself is stranger and more dynamic than we ever imagined. Our tools have evolved from naked eye observation to quantum sensors, from analog telescopes to digital observatories floating in space. And yet our core drive, the desire to understand our place in the cosmos, remains unchanged. As we stand at the frontier of new discoveries, from the hunt for life on exoplanets to the search for a unified theory of everything, we are reminded that our journey is far from over. In fact, it may have only just begun. The historical context of our cosmic understanding is not just a story of science and technology, but a testament to the human spirit, curious, resilient, and eternally reaching for the stars. You are a single human being, standing on a fragile planet that spins through a vast darkness, orbiting a star among hundreds of billions, in a galaxy among trillions, in a universe whose edge we cannot even see. And yet within you lives a mind capable of looking up, wondering, asking, dreaming. This is the reason why you should care. Because the universe is not just out there, floating beyond reach. It is also within you, etched into the particles of your blood, woven into the DNA of your bones, and echoing in the quiet chambers of your thoughts. And to ignore it would be to ignore a piece of yourself, a part of your own story that began not at your birth, but billions of years ago in the heart of a dying star, whose violent death scattered the heavy elements that would eventually become your body, your mind, your memories, and your soul. To care about the universe is to remember where you came from, and to acknowledge that everything you love, every person, every song, every feeling is balanced precariously on a thin atmosphere above a molten core, floating in the void, and that knowledge brings with it not just humility but awe, a deep and wordless recognition that life is rare, fragile, and infinitely precious. When we talk about distant planets or expanding galaxies or the birth of time itself, we are not merely talking about physics or astronomy. We are speaking to the deepest parts of what it means to be alive, to exist, to be conscious in a universe that, by all logical measures, should have been empty, silent, and dead. And yet here you are, reading these words, thinking your thoughts, beating your heart, a statistical impossibility made real by a universe that somehow allowed complexity to arise from chaos, structure from entropy, and life from dust. That mystery, how order could emerge from disorder, how atoms could assemble into thinking beings who then turn around and question the stasis, not just a scientific question, but an emotional one, a spiritual one, a human one. The vastness of the universe, the unimaginable scales of time and space do not diminish you. They give you context. They make your existence even more extraordinary, because in all that emptiness, you are here, alive, thinking. And that fact should make your breath catch in your throat, your skin tingle, your heart race, not out of fear, but out of reverence. And yes, there is fear too. There is the terror of insignificance, the fear that we are alone, or worse, that we are not. There is the dread that our world could be erased in an instant by forces we cannot predict or control, a rogue planet, a gamma ray burst, a black hole silently devouring everything in its path. And yet, even that fear connects us to something greater, because it means we are aware, we are vulnerable, we are real. The universe doesn't have to care about us, and most likely it doesn't, but we care about each other, and in that caring we define a kind of meaning that transcends the cold mechanics of space and time. The void out there is not just blackness and silence, it is a mirror, reflecting back our questions, our hopes, our need to know. Why are we here? What does it mean to be conscious? Is there life elsewhere? Are we the beginning of something or the end of something else? These questions are not trivia. They are the core of every religion, every philosophy, every piece of poetry ever written. The night sky has always drawn out our most intimate thoughts, not because it provides answers, but because it demands that we ask. And what a wonder that is to ask. That your brain, made of stardust and neurons, can imagine other worlds, theorize about the Big Bang, contemplate infinity. That your emotions can be stirred by a photograph of a galaxy millions of light years away. That you can look at a speck in a telescope and feel something. We explore space not just to learn facts, but because exploration is part of our nature. From the moment we left the trees and walked upright, we've moved forward across valleys, oceans, and now into the stars. Curiosity is our species' birthright. The same fire that made early humans paint constellations on cave walls is the same fire that launches rovers to Mars and probes to the edge of the solar system. When we stop caring about the cosmos, we are not just turning away from science, we are turning away from wonder, from possibility, from what makes us human. And space gives back so much more than knowledge. It gives us perspective. When you see Earth from orbit of blue marble suspended in darkness, you see no borders, no nations, no politics. You see a home, small and delicate, protected only by a thin blue line of atmosphere. That image changes people. It makes astronauts cry. It reminds us that we are all on the same ship, sailing through the same black ocean, clinging to the same fragile chance at existence. It connects us. And in an age when we are more divided than ever, the cosmos remains a unifying force, a shared mystery we can all look up to, regardless of our differences. Some people say we should focus on problems here on Earth before reaching for the stars. But that is a false choice. The tools we develop for space exploration, satellite imaging, telecommunications, medical devices, often come back and help us down here. More importantly, the inspiration of the cosmos gives us reason to solve our problems, to rise above our limitations, to imagine futures where we are not just surviving, but thriving. Every child who sees the rings of Saturn through a telescope, who watches a rocket rise on a plume of fire, who learns about galaxies and black holes and neutron stars, is given a gift, the gift of possibility, of dreaming bigger than what they see in front of them. And perhaps that is the most emotional reason of all to care. Hope. The universe is not finished. It is still evolving, still expanding, still unfolding in ways we do not yet understand, and so are we. There may be civilizations out there wondering the same things we are. There may be answers waiting in the dust of distant worlds. Or perhaps the journey itself is the answer, the act of wondering, the act of seeking. In the grand theater of existence, the universe does not hand out scripts. It simply offers the stage. And what a stage it is, spanning billions of light years, humming with the echoes of ancient stars, unfolding in patterns of chaos and beauty. We are players in that cosmic drama, and our awareness is the greatest plot twist of all. So, look up, not just with your eyes, but with your heart. Feel the weight of the mystery. Let it scare you. Let it move you. Let it fill you with questions that have no easy answers, because those questions are what make you more than just a passenger on this planet. They make you a participant in the story of the universe, a story that is still being written, and one that, if we dare to imagine, we might just help shape. What if everything you thought you understood about time, about existence, about your place in the cosmos was just the surface of something far deeper, something waiting to be uncovered, not in some distant lab, but within the questions you dare to ask? What if the hollow silence of the universe isn't silence at all, but a language we haven't learned to speak yet? A kind of cosmic whisper humming between the particles of your very body, waiting for you to stop, to listen, to wonder. Imagine, just for a moment, that the strange signals from planets like Z9079 aren't just anomalies in data, but deliberate markers left behind to provoke thought, like breadcrumbs scattered across the dark forest of the universe, leading us towards some truth that has eluded every civilization before us. What would that truth mean to you, not as a scientist, not as a skeptic or believer, but as a human being standing under a star-strewn sky, suspended in the mystery of everything? Could it be that the real frontier isn't space, but perception, the ability to see what's always been there, hidden not by distance, but by assumption? We have spent centuries constructing models of the cosmos, layering our knowledge like sediment, one discovery atop the last, each one revealing how staggeringly vast and strange this universe really is. And yet the more we know, the more obvious it becomes that we know almost nothing. So why stop? Why be content with the surface? Why not dive headfirst into the impossible? What lies beneath the surface of planets like Z9979? Could there be civilizations hiding in silence? Could advanced life choose to observe rather than communicate, to study rather than announce? And if so, how would that change the way we define intelligence, or consciousness, or even life itself? Would it still be alien, or would it simply be another expression of the same cosmic curiosity that drives us to build telescopes, launch probes, and scan the sky for signals that might never come? Are we truly the first, or just the latest, in a long chain of sentient species trying to make sense of a universe that may not want to be understood? And if we're not the first, what happened to the others? Did they disappear quietly, or did they find answers so profound that communication became unnecessary, irrelevant, even dangerous? We stand now on the precipice of a new era in exploration, not just technologically, but philosophically. The James Webb Space Telescope peers into the earliest moments of time. LIGO hears the thunder of colliding black holes. AI systems analyze patterns that human minds cannot grasp alone. We are building the tools not just to see the cosmos, but to understand it in a way that changes everything we thought was permanent. What happens when we detect life on an exoplanet, not as a vague signature, but as a deliberate paterna message encoded in biology or geometry or sound? What happens when we confirm that a planet isn't entirely natural, but modified, engineered, or constructed with intention? Do we celebrate? Do we panic? Do we change the way we educate, the way we pray, the way we see ourselves? And perhaps more urgently, how do we prepare for a universe that might be alive with intelligence when we can't even agree on the meaning of our own? These questions are not distant. They are here, now, pressing into the core of your thoughts. They're the reason you feel a chill when you watch the stars from a quiet hill. They're the reason children ask about black holes and other worlds and what happens when we die. These questions are the gravitational center of the human experience. We do not ask them because we expect answers. We ask because the asking itself defines us. The moment we stop questioning, we stop evolving. So ask yourself, what would it take for you to believe that we are not alone? Is it data? A signal? A face in the sky? Or is it a shift in your own mind? A willingness to let go of the neat boxes we've built around reality? Would you be able to accept that life elsewhere may not resemble anything we've imagined? Not humanoids, not creatures, but patterns of magnetism or light or time itself. And if life is out there in forms beyond our comprehension, isn't it also possible that the universe itself is conscious in ways we cannot yet define? That intelligence might not be confined to skulls or circuits, but embedded in galaxies, in physics, in the very act of existence. What if black holes are not just endpoints, but gateways? What if dark matter is not a missing mass, but a hidden structure? What if the void is not empty, but encoded? These are not idle speculations. These are the questions that scientists whisper when the data doesn't make sense, when the equations break down, when something is observed that cannot be explained within the framework of what we know. These are the conversations taking place in quiet labs and late-night messages between physicists, philosophers, and dreamers alike. And you, yes you, are part of that conversation, because every time you wonder even silent, you add to the great collective awareness that drives us forward. You are not just a spectator in this cosmic story. You are a contributor. Every question you ask is a flare fired into the darkness, lighting up a corner of the unknown, daring the universe to answer. And sometimes, it does not with certainty, but with mystery, with deeper questions, with paradoxes and possibilities that force us to evolve. So, how do you engage with this? Start by imagining. Not in a shallow escapist way, but in the deepest sense, let your imagination be the laboratory of your curiosity. What kind of civilizations might evolve on planets with different atmospheric chemistries? How would consciousness develop in beings who perceive time differently? What is the relationship between intelligence and survival, between observation and action? And most importantly, what does all this mean for us? Not just technologically, but morally, spiritually, personally? If we are not alone, how do we behave? If we are alone, how do we preserve what we've become? If the universe is more alive than we thought, how do we listen to it? How do we become worthy of hearing it? These are not questions for future generations. These are the questions of now. They belong to students who dream of becoming scientists. They belong to poets who look at stars and feel longing. They belong to people standing in silence at night, watching meteors streak across the sky and feeling something they can't explain. They belong to you. The more we learn about the cosmos, the more it challenges our assumptions not just about what's out there, but about what's inside us. Space is not just a vacuum of gas and stars. It's a stage for consciousness to ask itself who it is, where it came from, and what comes next. Every mystery we solve only uncovers greater ones. Every discovery is a doorway. Every answer leads to more beautiful, terrifying questions. And that is why we must talk about them, share them, debate them, let them disrupt our comfort and expand our wonder. Because the universe is not just strange, it is stranger than we can imagine. And we need all minds, all voices, all perspectives to help us even begin to grasp it. So the next time you see a story about a mysterious planet, a strange signal, a new discovery on the edge of known space-adont scroll past, ask yourself what it means. Ask others what they think. Spark a conversation not just about the science, but about what it feels like to live in a time where these questions are no longer fantasy, but reality. We are the first generation to see our universe in such detail, to know its age, its structure, its violence, and its beauty. But we may not be the last. What we do with this knowledge, how we share it, how we teach it, how we feel it will shape what comes next. The universe may be indifferent, but we are not. We care, we wonder, we search. And that, more than anything, is what makes us part of something greater. Not just stardust, but stardust that dreams. Out beyond the last breath of our solar system, past the Oort cloud's frozen halo and the echo of Voyager's fading signal, lies a darkness so pure and ancient that it bends our sense of time and meaning, a silence not born of absence, but of scale unimaginable, incomprehensible scale. The cosmos is not a quiet place, but to human ears and human minds, it seems like a vast cathedral of cold fire, where stars are candles, galaxies are stained glass windows, and the spaces between them the endless black air hymns in a language we've only begun to decipher. In this cathedral, everything is in motion, everything is alive, even the darkness. The Milky Way, our galactic home, rotates with a grace we cannot feel but can mathematically describe a swirling, spiraling sea of stars some 100 light-years across, containing over 200 billion suns, each with its own planets, its own histories, its own chance at life. And our sun is just one of those lights, nestled in a quiet suburban arm of this cosmic spiral, orbiting the galactic core at nearly 800 kilometers per hour, taking over 200 million years to complete a single revolution, dragging Earth and every dream it holds in its wake. Above and below this plane of stars lie the galactic halo and dark matter clouds, vast invisible scaffolds that shape and hold galaxies together with gravity we can measure but not see, hinting at a cosmic web that stretches across the known universe like ghostly sinews binding a skeleton of light. Between galaxies lies not emptiness, but void cements regions of space that can span hundreds of millions of light years, containing fewer galaxies than expected, regions so desolate that light can travel for eons without striking anything at all. These are the silent gaps between the bright clusters, places that defy comprehension, where the laws of physics still hold but seem to stretch and whisper, as if the universe itself is thinned there, translucent and strange. Then there are the phenomena too bizarre to belong to any stable narrative. Quasar Sultra, luminous beacons powered by supermassive black holes devouring matter at their cores, emitting radiation more powerful than entire galaxies. Pulsars, dead stars spinning so fast they flash beams of electromagnetic energy like celestial lighthouses. And gamma ray bursts, brief, deadly flashes from dying stars that can unleash more energy in seconds than our sun will in its lifetime. And behind it all, like an ancient pulse buried deep beneath the skin of space, is the cosmic microwave background, the afterglow of the Big Bang itself, still lingering, still detectable, as though the universe has never stopped remembering its own birth. To immerse yourself in this setting is to shed the scale of Earth, to let go of months and miles, and instead think in millions of years and billions of light years. To accept that the stars you see above were lit before your ancestors walked upright, and the ones being born now won't be visible to the naked eye until humanity itself evolves or vanishes. This is not science fiction. This is not metaphor. This is reality stripped of human-centered comfort and laid bare in all its terrifying, magnificent glory. And it is not empty of purpose. The universe is governed by laws, patterns, emergent properties that speak not of chaos, but of structure, of a kind of cosmic logic deeper than any one language. That logic has become the obsession of some of the greatest minds in history. In the 20th and 21st centuries, a new pantheon of scientific visionaries has taken up the challenge of decoding the cosmos. Edwin Hubble, who proved the universe was expanding, looked into the eyes of distant galaxies and saw movement, a breath of space itself. George Lemaitre, the priest physicist, first proposed the primeval atom, the model that became the Big Bang. Stephen Hawking, whose mind soared while his body remained imprisoned, mapped the behavior of black holes and time, suggesting that even singularities have a story to tell. Vera Rubin, often overlooked, gave us one of the most transformative insights of all the confirmation of dark matter, based on the rotational curves of galaxies, forcing us to accept that most of what exists in the universe is invisible, and yet undeniably there. More recently, names like Kip Thorne, Max Tegmark, Brian Greene, and Sean Carroll have pushed the frontiers of theoretical cosmology, exploring ideas such as the multiverse, quantum gravity, and the possibility that time itself is emergent rather than fundamental. They do not all agree. They argue, they revise, they pursue proofs that sometimes vanish at the edge of what can be tested. But they are all pulled by the same gravity, the desire to understand, to explore, to peel back the fabric of reality and look beneath. In their labs, in their equations, in their lectures to the public, they speak of things once reserved for prophets and poets. They speak of dimensions beyond our senses, of space-time bending and curving and tearing. They describe inflation and era in the earliest fractions of a second after the Big Bang, when the universe ballooned faster than light itself, and entropy, the arrow of time, the slow drift toward disorder that seems etched into everything from a cooling cup of tea to the dying heat of stars. And they are not alone. Engineers build machines to match their vision. The Hubble Space Telescope, the Chandra X-ray Observatory, the James Webb Space Telescope, and future missions like the Nancy Grace Roman Space Telescope and the Laser Interferometer Space Antenna, LISA. All these instruments are eyes extended into the void, seeing light too faint, too distant, or too strange for human eyes. Each image they send back is a doorway to another time, another structure, another mystery, a star exploding, a galaxy merging, a black hole dancing. We think of space as silent, but it sings in spectroradio, infrared, ultraviolet, gamma, each a layer of reality translated by instruments into data, then into understanding, then into awe. And what is awe, if not the purest expression of curiosity tinged with humility? It is the awareness that you are small, but not irrelevant, that you are brief, but not meaningless. To feel awe is to be present at the altar of something bigger than comprehension. It is to watch a supernova animation and realize that it has happened, is happening, will happen again, blowing apart star systems, scattering the building blocks of life into a universe that may or may not care. And yet, we care. We care enough to name stars, to send messages into space, to spend billions of dollars and decades of our lives building machines to catch particles that barely exist: neutrinos, gravitational waves, dark photons. We care because deep down we know the greatest mystery of all is not the universe, it is us within it. For in the quiet middle of this vast symphony, we exist. Fragile, curious, brilliant, terrified. We build observatories inside mountains and under ice. We launch rovers across alien deserts. We decode the radiation left over from the Big Bang like archaeologists brushing dust off a mosaic. And we tell stories. Not just myths anymore, but models: mathematical, falsifiable, predictive. We write the universe in symbols and code, looking for patterns that might reveal its soul. And what we find changes us. Every discovery challenges not just our science, but our identity. Earth was not the center of the universe. Then the sun wasn't either. Then the galaxy. Then the visible universe. We have been displaced again and again. And yet in that displacement, we have found perspective, a more honest place, a more powerful place, a place where we are not rulers of the cosmos, but its witnesses. So stand with me at the edge of this cosmic shore. The sea before us is deep and black and endless. Behind us, the fires of understanding warm our backs. We carry maps, etched in mathematics, telescopes built of glass and gold, minds sharpened by centuries of wonder. But the ocean does not end, and neither does the sky. We do not know what we will find. Perhaps echoes of other minds, perhaps reflections of our own, perhaps questions we cannot yet frame. But we will keep going, because the universe is not just a place. It is a mirror, a question, a companion in our deepest longing to know. And when you look up at the stars tonight, do not see them as distant. See them as invitations. Each one is a light lit long ago, traveling unimaginable distances just to reach your eye. Each one is a reminder that you are part of this, that the atoms in your breath were forged in ancient fire, that the darkness is not the end of something, but the beginning, that the story is still unfolding, that you are not just looking at the universe, you are a way for the universe to look back at itself. From the very first moment we pointed instruments at the sky, we were faced with limits, some obvious, others subtle, but all pointing to a deeper truth, that for all our progress, there may be questions the universe simply will not allow us to answer. The idea of an edge to the universe has haunted human thought for millennia, and even now, with all our scientific sophistication, we remain uncertain if such an edge even exists, whether in space, in time, or in comprehension itself. We chase it not just because we're curious, but because our nature demands closure, boundaries, definitions. But the more we look, the more the horizon recedes. Every measurement we take is filtered through the narrow aperture of human perception and the physical laws that govern what we're allowed to observe. Our light speed limit, the quantum uncertainty principle, the observer effect, the expansion of space itself, each forms a kind of veil, a curtain that grows more intricate the closer we try to peer beyond it. This is not just a technological problem, it's philosophical, existential, and perhaps even structural. From the very first deep sky observations made by Edwin Hubble, we discovered that galaxies were not static, they were fleeing from us. The farther away they were, the faster they receded. This wasn't because Earth held a privileged place in the cosmos, but because space itself was expanding. That single discovery shattered our notions of a fixed, eternal universe. But it also introduced the first great paradox. If the universe is expanding, what is it expanding into? If everything is moving outward, where is the center, and what lies beyond? The answer, as far as current physics can tell, is that the universe has no center and no edge. It is not expanding into anything, it is simply expanding. But that explanation, though mathematically sound, offers no emotional resolution. It runs up against the boundary of imagination. where our need for spatial intuition breaks down entirely. And the limitations don't end there. The observable universe is finite not because the cosmos itself is necessarily bounded, but because light has only had 13.8 billion years to travel since the Big Bang. Due to the expansion of space, this means we can see out to roughly 46.5 billion light-years in any direction. Beyond that, we don't know. We can't know. The light from beyond that limit has not had time to reach us and may never reach us, due to the accelerating expansion caused by dark energy. So even if the universe stretches on forever, to us it may as well not exist. Our observable bubble is both our window and our prison. And here lie the early seeds of conflict, the paradoxes that accumulate when we try to describe something fundamentally greater than ourselves with tools forged from within the system we're trying to observe. Think of quantum mechanics, where particles exist in multiple states at once, only collapsing into a definite form when observed. Or general relativity, where time is relative, stretched and compressed by gravity. Each framework is internally consistent, and yet, when combined, they clash. Gravity and quantum theory refuse to reconcile, giving rise to contradictions that hint at missing pieces in our understanding of the cosmos. Every major theory we have is, in some sense, provisional. Newton's elegant laws of motion were upended by Einstein's relativity. Classical thermodynamics faltered under quantum probability. The standard model of particle physics, while accurate in predictions, cannot explain dark matter, dark energy, or gravity itself. Even the Big Bang, our best explanation for cosmic origin, contains within it questions we cannot resolve. What caused it? What came before it? Can we even speak meaningfully about a before in the absence of time? These aren't just semantic problems, they are structural impasses. They arise from the deep architecture of the cosmos, where our language, our math, our measurements may simply not be enough. And our instruments, magnificent as they are, share our limitations. Telescopes cannot see through dust clouds without switching to infrared. They cannot detect gravity waves unless the events are cataclysmic. They cannot observe objects below a certain brightness or smaller than a certain size. There are entire categories of phenomena that could exist, right now, beyond our detection threshold, not because they are supernatural, but because they operate on scales or energies our current tools cannot reach. There is also the problem of interpretation. The data we do collect must be filtered through human analysis hypotheses, models, predictions. These are subject to bias, error, and assumption. Scientific consensus is built over decades, often shifting dramatically as new evidence arrives. Consider the shifting status of the cosmological constant from Einstein's greatest blunder to a cornerstone of dark energy theory, or the reclassification of Pluto, which was once the 9th planet and now isn't. These changes reflect growth, but they also reveal instability in our definitions. The universe resists neat labels. It refuses to stay inside the boxes we build for it. The deeper we dig, the stranger things become. At the quantum level, particles pop in and out of existence, entangle across vast distances, behave like waves and particles simultaneously. At the cosmological level, the fabric of space itself stretches and bends, and the vacuum is not empty but seething with potential. The further out we look, the further back in time we peer, until we see the afterglow of the Big Bang itself, a faint, frozen light, mapped with exquisite precision, yet still not fully understood. Even time itself, so foundational to human experience, may not be fundamental. Some physicists propose that time emerges from entropy or from the arrangement of quantum states. Others suggest that our arrow of time is a local illusion, one that could break down under extreme conditions, such as near a black hole or at the birth of the universe. Black holes themselves are paradoxes incarnate to regions where the known laws of physics collapse under their own weight. At their core, we face a singularity, infinite density, zero volume, where space-time curvature becomes infinite. General relativity predicts this, but quantum mechanics cannot tolerate it. This inconsistency has become one of the greatest tensions in modern physics. The attempt to resolve it has led to string theory, loop quantum gravity, holographic principles, and more. None have yet triumphed. Each offers tantalizing glimpses, but each also brings new questions, new abstractions that grow ever more detached from empirical testability. And so, the edge of understanding is not just spatial, it is methodological. There may come a point where the phenomena we seek to understand require energies, distances, or dimensions we simply cannot access. No particle accelerator will ever replicate the conditions of the first Planck moment after the Big Bang. No telescope will ever look beyond the cosmic horizon. We are chasing shadows cast by forces that existed before our atoms were forged. And yet, we persist. Because the nature of science is not certainty, but curiosity. Every paradox is a clue. Every limitation is a challenge. The tension between what we know and what we can know is the very fuel of discovery. But we must confront the possibility that some questions may never be answered, not because they are invalid, but because they lie beyond the reach of experiment and observation. We may develop theories that are internally perfect, mathematically beautiful, logically coherent, but if they cannot be tested, then they remain in the realm of speculation. And this leads us to a deeper conflict: the clash between human desire for ultimate truth and the universe's apparent refusal to provide it. What if there is no final theory? No grand unification waiting to be found? What if the universe is inherently fragmented, emergent, recursive, endless puzzle where each solution births another mystery? Would we be content with that? Could we learn to embrace uncertainty, not as a failure of knowledge, but as a fundamental feature of reality? Or would we keep searching, ever driven by the hope that just beyond the next telescope, the next collider, the next theory lies the answer we seek? The concept of the edge becomes both metaphor and map. It is the line we walk between known and unknown, seen and unseen, possible and impossible. And every step forward reveals not a boundary, but a deeper fog. In that fog lie the greatest philosophical questions we've ever asked. Are the laws of physics constant, or do they vary across the multiverse? Is the universe fine-tuned for life? Or are we just the lucky outcome of a cosmic lottery? Do we have free will in a deterministic cosmos? Can consciousness be explained by neurons and particles alone? These questions are not distractions from science, they are its culmination. For science, at its highest level, is not just about explaining what is, but confronting the limits of explanation itself. And so, as we stand on the precipice of discovery, launching new telescopes, decoding gravitational waves, scanning the sky for exoplanets, hunting for the signature of alien intelligence, we must also prepare ourselves for the reality that the edge may never be reached. That for every layer we peel back, another lies beneath. That the universe is not a puzzle with a single solution, but a living, breathing mystery, one that reveals itself only partially, like a dream remembered in fragments. This is not defeat. It is wonder. It is the essence of awe of the feeling that comes not from having all the answers, but from realizing how much more there is to ask. So we continue not despite the limitations, but because of them. Because each paradox is a doorway. Each contradiction is a map. And even if we never find the true edge, we will draw closer to something even more profound. The realization that in the act of seeking, we fulfill our most ancient purpose, not to conquer the universe, but to commune with it. To become, for a brief and shining moment, a conscious flicker of the cosmos, daring to ask the impossible question. The deeper we peer into the cosmos, the more we realize that the universe does not hand over its secrets easily. With each breakthrough comes a wave of new questions. Each discovery spawns a dozen paradoxes, and as our telescopes grow stronger and our equations more refined, so too does the conflict at the heart of cosmologia. Conflict between brilliant theories that often refuse to coexist, between what we can observe and what the math demands, between the finite tools of human perception and the infinite scales of cosmic reality. At the core of this conflict lies one question that has haunted science for decades, perhaps centuries. Is the universe infinite, or is it finite? Does it stretch endlessly beyond our observational limits, or does it loop back on itself like a cosmic sphere? This is not a trivial matter of geometry. It is a battle of worldviews, of how reality itself is structured, and the tension has never been more intense. General relativity, Einstein's masterwork, offers us a flexible, dynamic model of space-time shaped by mass and energy. It allows for a range of cosmic geometry. Often flat, closed-end. For decades, cosmologists have debated which one describes our reality. The data, particularly from the cosmic microwave background, CMB, suggests that the universe is flat to within a very small margin of error. But flat in this context doesn't mean simple. It means that parallel lines remain parallel, that space isn't curved at large scales, and that the universe could very well be infinite. Yet even this apparent simplicity hides a war beneath the surface. If the universe is infinite, what does that mean for matter, for structure, for life? Does every possible configuration of atoms occur somewhere, repeated endlessly across infinite space? Are there infinite Earths, infinite versions of you, playing out every permutation of your life in parallel by sheer statistical inevitability? This idea, supported by the principles of inflationary cosmology and quantum mechanics, leads to the unsettling conclusion that not only is the universe vast, but perhaps everything that can happen has already happened somewhere. And yet this notion is not universally accepted. Many physicists balk at the idea of actual infinities, pointing out that they break down logic, cause paradoxes, and render probabilities meaningless. Infinity is not a number, it's a concept, a limit. In physical terms, some argue, it has no place. They propose that the universe is finite but unbounded, like the surface of a sphere limited in volume, but without edges. You could travel forever without hitting a wall, looping through the curvature of space endlessly. But even this elegant model has problems. If the universe is finite, how did it become so large in just 13.8 billion years? The theory of cosmic inflation, a rapid exponential expansion in the universe's first moments, was introduced to solve this, along with several other cosmological puzzles. It explains the smoothness of the CMB, the apparent flatness of the universe, and the absence of magnetic monopoles. But inflation theory is not a single theory. It's a framework with countless variants, many of which predict an eternal inflation scenario, where our observable universe is just one bubble in a foam of countless others, each potentially with its own laws of physics, constants, and dimensions. This multiverse interpretation is powerful, but it raises profound issues. If other universes are forever beyond our observational reach, can their existence be considered scientific at all? Are we crossing from physics into metaphysics, from evidence into speculation? Some physicists defend this direction, arguing that if a theory is mathematically consistent, fits our data, and makes predictions, it should be considered valid even if we can't directly observe all its consequences. Others fiercely disagree, holding that science must be grounded in falsifiability, in observable, testable outcomes. This divide has deepened as theoretical physics has moved further from direct experimentation. String theory, for example, seeks to unify gravity with quantum mechanics, positing tiny vibrating strings as the fundamental constituents of reality. It's elegant, comprehensive, and offers a framework for a finite or infinite universe, but it has yet to make a single prediction that can be tested with current technology. In the same camp lies the holographic principle, born from studies of black hole entropy and quantum information, which suggests that the entire universe may be a projection of 3D reality encoded on a 2D surface, like a cosmic hologram. This idea, while shocking, is mathematically consistent with what we know about black holes and quantum mechanics. But again, it sits at the edge of what can be tested. Meanwhile, observational cosmologists struggle to interpret the vast flood of data pouring in from missions like Planck, WMAP, Hubble, and JWST. They map the sky, measure redshifts, catalog galaxies, and analyze the CMB, seeking the fine patterns that might distinguish between competing models. They find anomalous cold spots, unexpected alignments, large-scale flows that don't quite fit the standard model. Are these statistical flukes or signs that our theories are incomplete? Are we looking at echoes of another universe colliding with ours, as some inflation models suggest? Or are we seeing the limits of our observational tools, the imperfections of our instruments, the biases of our algorithms? The conflict grows deeper when we examine the behavior of matter and energy in the universe. Ordinary matter, the kind that makes up stars, planets, and people, accounts for only about 5% of the total. The rest is dark matter and dark energy, two phenomena we can infer through their gravitational effects, but cannot detect directly. Dark matter explains the rotation curves of galaxies, the motion of clusters, the formation of large-scale structures. But despite decades of searching, no dark matter particle has been conclusively identified. Is it a new kind of particle? A modification of gravity? A mirage caused by unknown quantum effects? Dark energy is even more mysterious. It's driving the accelerated expansion of the universe, pushing galaxies apart faster and faster. But we don't know what it is. Is it the cosmological constant Einstein once proposed and rejected? A field-like quintessence that evolves over time? A sign that general relativity itself needs revision? Some physicists believe dark energy may not exist at all, that the apparent acceleration is a misreading of the data caused by cosmic inhomogeneities. If they are right, the universe might not expand forever. It might slow down. It might even collapse. And so the edge becomes not just a spatial question, but a temporal one. Will the universe expand eternally, growing colder and emptier until even atoms decay in a heat death? Will it tear itself apart in a big rip? Will it cycle through big bangs and big crunches in an eternal recurrence? Each scenario depends on parameters we are still struggling to measure, and the theories we use to describe them do not always agree. Even within the same scientific communities, different camps argue over foundational concepts. Some see gravity as emergent statistical effect of microscopic information processing. Others insist it is a fundamental force woven into the fabric of space-time. Some seek a unifying theory of everything, while others suggest the quest itself may be misguided based on assumptions about unity that nature may not share. This fragmentation is not a failure of science. It is a sign of its health, its dynamism, its willingness to question itself. But it is also a source of tension, intellectual, emotional, and philosophical. For cosmologists, the edge is more than a line in the sky. It is a battleground of ideas, a place where logic breaks and visions collide. It is the point where we must ask whether reality is knowable in the way we once believed. And it is here, in this crucible of contradiction, that the future of cosmology will be forged. Will we discover new principles that reconcile quantum mechanics with gravity, that illuminate dark matter and dark energy, that reveal the shape and fate of the universe? Or will we reach a plateau, a boundary, beyond which no further understanding is possible? Some fear this outcome. Others embrace it. For even if we never find the edge, the journey itself has transformed us. We have mapped the universe's history from a fraction of a second after the Big Bang to the birth of stars and galaxies. We have seen black holes collide, heard the ripples in space-time, and traced the afterglow of creation. These are not small things. They are miracles of insight, feats of collaboration, triumphs of imagination. And they suggest that, despite the conflict, despite the limits, we are closer than ever to touching the infinite. The universe is not a riddle with one answer. It is a symphony of theories, a dance of evidence and imagination, a dialogue between what is seen and what is guessed. It resists conclusion, not out of cruelty, but because its story is still being written, and we are the writers. Each contradiction is a paragraph, each experiment, a sentence, each mystery, a breath. The edge may remain forever out of reach, but in reaching, we become something more. We become the conflict it's alive, unfolding, brilliant in our defiance of the unknown. If the universe has no edge and no boundary, no outer wall, no final frontier where space ends and something else begins, then our understanding of existence must shift in ways more profound than any previous scientific revolution. We have long imagined frontiers. From the boundaries of continents to the edge of the solar system, our exploration has been shaped by the assumption that something lies beyond the known, that there's always a border to cross, a next place to reach. But a universe with no edge presents a radically different picture. One where the frontier never ends, not because it is always just beyond reach, but because it doesn't exist at all. And this idea, while abstract, carries consequences that ripple through every layer of science, philosophy, and even the core of human identity. The implications for physics and cosmology are staggering. If there is no edge to the universe, if space itself stretches infinitely in all directions, or loops back on itself in a closed, boundaryless topology, then many of our foundational models must be re-evaluated. Current theories in cosmology hinge on the structure of space, the geometry of the universe, and the initial conditions of the Big Bang. The notion of an infinite or edgeless universe challenges our ability to define total energy, volume, or even a meaningful average density of matter. In a finite universe, we can imagine counting galaxies, adding up their masses, calculating ratios of matter to energy. But in an infinite universe, these quantities become undefined, or at best, localized approximations with no global certainty. We're forced to operate in models that work on observable scales, while acknowledging that they might be utterly unrepresentative of the total cosmos. This leads directly to a crisis in cosmological modeling. Take the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. It has served us well in building simulations and interpreting observations. But it's an assumption, not a proven truth. In an infinite universe, the idea of average density is meaningless without boundaries to define the system. Moreover, if space goes on forever, then even the rarest events like galaxies forming identical to the Milky Way or civilizations evolving with the same thoughts, languages, or histories will occur again. Infinitely, many times. Every configuration of matter permitted by the laws of physics would be realized, not once, but an infinite number of times. In other words, an edgeless universe demands that we confront the possibility of infinite repetition, where versions of Earth and versions of ourselves recur endlessly. These duplicates are not science fiction, they are statistical certainties in a truly infinite cosmos. That alone challenges our concept of identity, uniqueness, and free will. Are we just one of countless copies, each believing it is the original? Do our choices matter in a universe where every choice is made somewhere? From a scientific standpoint, this pushes the boundaries of what physics can meaningfully describe. It introduces the anthropic principle where the universe appears the way it does because observers like us exist to see it not as a philosophical musing, but as a necessary tool for reasoning in a multiverse or infinite space. It also suggests that our current models, while accurate within our observable bubble, may be profoundly incomplete. General relativity works well on large scales. Quantum mechanics governs the small, but these two pillars of modern physics refuse to unify. A universe with no edge, where curvature may not resolve into any final topology, demands a new framework, new physics that can handle both gravity and quantum uncertainty, space and time, infinity and entropy, without contradiction. This is the dream of a theory of everything, long pursued and never attained. And perhaps that dream remains out of reach because the universe itself resists simplification. Perhaps our assumptions about unity, symmetry, and order are projections of the human mind, not reflections of cosmic truth. Philosophically, the absence of an edge alters our relationship with reality. Throughout history, we have used boundaries, physical, temporal, and metaphysical, to give meaning to life. The edge of the world, the end of time, the border between the living and the dead, these concepts have shaped religion, art, morality, and identity. To live in a universe without an edge is to inhabit a space with no end, no privileged position, no final resting place. It removes the notion of beyond as a spatial concept and replaces it with a continuum. There is always more. No matter how far you go, you are still in the middle of something. This can be freeing, but also terrifying. Without an edge, where does creation stop? Where did it start? The Big Bang is often misimagined as an explosion from a single point outward into emptiness. But in truth, it was not an explosion in space, it was an expansion of space. If the universe is infinite now, it was infinite then. That breaks our intuition. How can something infinite expand? how can infinity get bigger? It forces us to consider that time and space, as we experience them, are not fundamental features of reality, but emergent property solutions born from deeper, unknown dynamics. Quantum gravity theories like loop quantum cosmology and string theory suggest space-time might be granular, composed of tiny, discrete units. Others propose that time doesn't exist at all on the most fundamental level, that it's a useful construct for beings like us, evolved to perceive cause and effect, but ultimately not real. A universe without edge strengthens these arguments. It suggests that our senses, our symbols, our entire language of description is shaped by limitations of scale, energy, and perception. We cannot trust our gut. We cannot trust our metaphors. We must let go of what makes sense and embrace what the math, the data, and the implications are trying to show us, even if they feel alien, even if they make us question the very nature of what it means to know. Existentially, this edgeless cosmos can be both a burden and a beacon. It diminishes humanity's centrality in the grand scheme. It implies that life, even intelligent life, is not a miracle of rarity, but an inevitable product of chemistry repeated across infinite worlds. This can make us feel small, insignificant, but it can also ennoble us. Because even if there are infinite versions of you somewhere in the cosmos, none of them are here, right now, feeling what you feel, thinking what you think, standing under the stars with the specific memories and emotions that make up your identity. The absence of edges doesn't erase, meaning it transforms it. Meaning becomes local, personal, chosen. And that perhaps is more powerful than inherited or imposed purpose. We live in a universe without boundaries, but we are creatures of boundary. Our lives are finite, our bodies have edges, our time is brief. And it is precisely this contrast, the infinite surrounding the finite, that gives our existence its emotional weight. In a way, we are the edges. We are the points at which the cosmos pauses to reflect on itself. But if we are to carry that awareness forward, if we are to continue exploring, understanding, and evolving, we must acknowledge that our current physics is not enough. The Standard Model, for all its elegance, cannot explain gravity, cannot account for dark matter, cannot unify with general relativity. Inflation theory, for all its successes, is still a hypothesis, a powerful one, but one with untested assumptions. The concept of space itself, once thought to be an empty stage, is now a dynamic participant in the cosmic drama. And time? Time may be the greatest illusion of all. To confront a universe without edge is to confront the edges within ourselves, our intellectual limits, our fears, our assumptions. It calls for a radical humility, a willingness to discard cherished ideas and embrace frameworks that might feel unnatural or incomplete. This is not a call to nihilism. It is a call to wonder. Because even in its unknowability, the universe is generous. It offers us light from the past, particles from the stars, clues etched into the patterns of galaxies and the decay of atoms. It gives us mystery, not to frustrate us, but to draw us out of comfort into the possibility of transformation. If there is no edge, then every place is the center. Every observation matters. Every theory is a step toward a deeper horizon. And every person is a kind of mirror, reflecting back the universe's own urge to question, to imagine, to become. In the coming decades, we may discover particles that explain dark matter. We may develop a testable theory of quantum gravity. We may map the large-scale structure of the universe with enough precision to glimpse its true shape. But we must also be prepared for the opposite, for the realization that some things are fundamentally unknowable, not because we are failing, but because the nature of reality resists complete containment. An edgeless universe does not mock our efforts. It invites them. It dares us to be bold, to reimagine physics not as a quest for closure, but as a celebration of the infinite unfolding of curiosity. And so we continue not because we expect a final answer, but because we are the question, walking through an endless cosmos, carrying the fire of wonder. The story of the universe was once thought to be a tale with a beginning, a middle, and an inevitable end, a singularity that exploded into existence, forming stars and galaxies, slowly cooling and spreading out into nothingness. For decades, cosmologists believe that the universe would eventually halt its expansion, held in check by gravity, and reverse into a catastrophic collapse, Big Crunch. But at the close of the 20th century, a discovery so unexpected, so profoundly disruptive, changed everything. It was a moment of reckoning for physics, a turning point that continues to reshape our understanding of reality. That discovery was dark energy. In 1998, two separate teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Teamware studying type Ia supernovae, stellar explosions so bright they could be seen across billions of light years. These supernovae serve as standard candles, their intrinsic brightness known and constant, allowing astronomers to measure cosmic distances with remarkable accuracy. The goal was to determine whether the universe's expansion was slowing down due to gravitational pull. What they found instead was astonishing. The supernovae were dimmer than expected, suggesting they were farther away than they should be. The universe wasn't decelerating, it was accelerating. This revelation shook the foundations of cosmology. It implied the presence of a mysterious force counteracting gravity on the largest scales, a repulsive energy embedded in the very fabric of space. This force was dubbed dark energy, and subsequent measurements revealed it accounts for roughly 68% of the total energy content of the universe. Along with dark matter, about 27%, and ordinary matter, a mere 5%, dark energy became the dominant player in the cosmic drama. It was as though we had been reading a novel and suddenly realized we'd misidentified the main character. The nature of dark energy remains elusive. It may be Einstein's cosmological constanta uniform energy density inherent to space itself, or it may be a dynamic field, like quintessence, that changes over time and space. It may not be a force at all, but a signal that general relativity needs to be modified on cosmological scales. Whatever it is, its effect is undeniable. It stretches space, causes galaxies to accelerate away from one another, and dictates the ultimate fate of the universe. If dark energy remains constant, the cosmos will continue expanding forever, galaxies drifting apart until only the cold afterglow of the Big Bang remains. If it increases, the universe may tear itself apart in a violent and the Big Rip. If it weakens or reverses, we might yet see a return to contraction. These are no longer theoretical games, they are the real consequences of real observations. To understand dark energy and the deeper structure of the cosmos, we needed better tools, and we built them. One of the greatest technological achievements of the modern era is the Hubble Space Telescope. Launched in 1990, it revolutionized our view of the universe. Hubble captured breathtaking images of distant galaxies, nebulae, and deep field exposures, showing thousands of galaxies in a single frame each, a city of stars. But beyond the images, Hubble provided precise data on galaxy distances and redshifts, helping establish the accelerating expansion of the universe and refining the value of the Hubble constant, the rate at which space expands. Yet Hubble was just the beginning. The James Webb Space Telescope, JWST, launched in 2021, represents the next great leap. Designed to observe in infrared, JWST can peer through cosmic dust and see light from the earliest galaxies, formed just a few 100 million years after the Big Bang. Its sensitivity and resolution dwarf Hubble's, allowing scientists to study the atmospheres of exoplanets, probe the structure of galaxies, and refine our models of cosmic evolution. Within its first year, JWST delivered surprises. It found galaxies at high redshifts that were more massive and mature than current models predicted. How could such structure form so quickly in the early universe? This unexpected finding has triggered a re-evaluation of the timeline of galaxy formation and the processes that drive it. It suggests that the universe may have formed stars and black holes more efficiently than we thought, or that our understanding of early cosmic conditions is incomplete. Other missions have added depth to this picture. The Planck satellite provided the most detailed map of the cosmic microwave background, revealing the universe's composition, curvature, and initial density fluctuations. These tiny variations, imprinted on the CMB, seeded the formation of galaxies and clusters. Planck confirmed the flatness of space, the dominance of dark energy, and the validity of the inflationary Mandela period of rapid expansion in the first fraction of a second after the Big Bang. The data fit the model well, but not perfectly. Anomalies remain, a cold spot, unexplained alignments, and statistical deviations that resist easy explanation. These could be artifacts, or they could be hints of new physics. Meanwhile, gravitational wave astronomy has opened a new window. LIGO and Virgo, the twin detectors that first observed the ripples in spacetime caused by merging black holes, have inaugurated an entirely new method of observation. Gravitational waves are not blocked or scattered like light. They pass through matter and emerge unchanged, offering a pristine view of cataclysmic events. In the future, space-based detectors like LISA will detect waves from supermassive black hole collisions, and possibly even the primordial waves from inflation itself if they exist. Such a discovery would be revolutionary, offering direct insight into the earliest moments of the universe, when quantum mechanics and gravity dance together in ways we do not yet understand. Each new technological step pushes the boundary of the observable, revealing a universe more complex, more dynamic, and more mysterious than we imagined. We have discovered that galaxies do not merely exist in isolation. They are part of vast filaments, stretching across billions of light years, forming a cosmic web. We have found exoplanets in abundance, thousands of them, some Earth-like, some wildly exotic. We have mapped dark matter indirectly through gravitational lensing, observing how it bends light and shapes structure. These findings all point to a universe that is not static, not sterile, but alive with structure, history, and potential. And they bring us back to the turning point. Because the deeper implication of all these discoveries is not just that the universe is bigger or older or stranger, it's that our current physics, powerful as it is not complete. The standard model of particle physics explains 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force with astonishing precision. But it cannot explain gravity. It cannot explain dark matter. It cannot explain dark energy. It has no place for the accelerating expansion of the universe. Nor does general relativity, for all its elegance, offer answers about the quantum realm, or about what happens inside black holes, or before the Big Bang. We are at the edge of our models. And the turning point is not just technological, it is conceptual. We are entering a phase where physics must evolve. We need a theory of quantum gravity. We need to understand the vacuum of space not as emptiness, but as a seething foam of virtual particles and energy fields. We need to reconcile the smooth, continuous fabric of space-time with the granular, probabilistic world of quantum mechanics. And we must do so in the context of a universe shaped by dark energy, a force that seems to oppose gravity, accelerate space, and perhaps even originate from the energy of empty space itself. This is a formidable challenge, but it is also a moment of opportunity, a chance to reshape our understanding of reality at the deepest level. The turning point is not a single event, it is a convergence, a collision of data, theory, and technology, a recognition that we stand on the edge of a deeper horizon. And in this moment, the role of humanity becomes clearer. We are not passive observers. We are not insignificant. We are the only known beings who ask these questions, who build instruments to look beyond themselves, who seek understanding not for survival, but for its own sake. We are the cosmos becoming conscious of itself. And this consciousness has now glimpsed a truth it cannot ignore, that the universe is expanding not just in space, but in meaning, that the more we know, the more we realize what remains unknown. Dark energy may be the thread that unravels our old models. It may be the key to a deeper understanding of space-time, of the birth of the cosmos, of the nature of reality. Or it may be a signpost, pointing us to phenomena we have not yet imagined. Either way, we are now in a new Iran era, defined not by what we see, but by how we interpret it. Our instruments have given us vision, our theories have given us structure, but it is our curiosity that gives us purpose. The universe did not have to be observable. It did not have to be comprehensible. Yet somehow, it is both. And that miracle of clarity, however partial, however fleeting, is the turning point we now live in. It is the moment where the questions become bolder, the stakes become higher, and the answers, however incomplete, begin to reshape what it means to be human. For centuries, humanity has tried to answer the great questions of existence by looking outward into the night sky, into the cosmos, into the depths of time and space. We built telescopes to see further, satellites to probe deeper, and equations to describe it all. Our models have grown more sophisticated, our tools more precise, and yet a persistent sense of incompleteness remains. We've mapped the observable universe, studied the cosmic microwave background, and identified the accelerating expansion driven by dark energy. But in the face of mounting paradox contradictions between quantum mechanics and general relativity, the mystery of dark matter and dark energy, the quantum vacuum, and the unsolved unification of forces, a new possibility is emerging. That we may be looking at the entire problem the wrong way. That the universe, as we perceive it, may not be fundamental. That space and time may be emergent phenomena. And that we might live not in a three-dimensional reality as it appears, but on the edge of something deeper, stranger, and entirely unlike anything we imagined. This radical idea has been gaining traction under the name of the holographic principle, a theory that emerged from studies of black holes and quantum gravity. The principle suggests that everything we perceive as three-dimensional may actually be a projection of information encoded on a two-dimensional surface, a cosmic hologram. The idea was born from the physics of black holes. In the 1970s, physicist Jacob Bekenstein proposed that the entropy or information content of a black hole was proportional not to its volume, but to the area of its event horizon. Stephen Hawking's calculations soon confirmed that black holes radiate energy, now known as Hawking radiation, which means they must lose mass over time. This created a paradox. If black holes eventually evaporate, what happens to the information they contain? In physics, information is supposed to be conserved, but the mathematics seem to suggest it would vanish forever. That contradiction led physicist Gerard Tooft and later Leonard Susskind to propose a solution. The information inside a black hole might not be lost, but instead stored on its surface, just like a hologram, where a 2D pattern stores all the information needed to reconstruct a 3D image. The implications were staggering. If the information content of a region of space is encoded on its boundary, then perhaps this isn't just true of black holes but of the entire universe. According to this view, our three-dimensional reality, including time, might be a projection of quantum information encoded on a distant, lower-dimensional boundary. In this perspective, everything we experience, matter, energy, space, even consciousness, could be the emergent result of information processing taking place on this screen beyond our perception. The holographic principle is not mere speculation. It is mathematically grounded, supported by studies in string theory and quantum field theory. The ADS CFT correspondence, formulated by Juan Maldacena in 1997, demonstrated a precise equivalence between a theory of gravity in a higher dimensional bulk and a quantum field theory on its lower dimensional boundary. Though ADS CFT applies to a universe with a very specific curvature, anti-de Sitter space, it was a concrete example of the holographic principle in action. This shift in perspective is more than mathematical. It challenges the foundational assumptions of physics and cosmology. It suggests that space is not a backdrop, but a constructed emergent feature arising from deeper, more fundamental rules. It challenges our understanding of what real means. If what we perceive is a projection, what lies beneath the surface? Are we capable of seeing it, or are we forever trapped inside the image? This idea finds resonance with other radical theories. Some physicists believe time itself may not be fundamental, but emergent arising from entanglement and thermodynamic relationships. Others propose that space-time geometry is a kind of network or graph generated by quantum information interactions. Concepts like loop quantum gravity, spin networks, and quantum graphity propose a discrete structure to space at the smallest scales, replacing the smooth continuum of general relativity with a granular, pixelated geometry. These theories point toward a different kind of universe, one where space, time, and even matter arise from a vast sea of information. and where the laws we observe are the statistical outcomes of deeper patterns. This reinterpretation of reality affects how we understand not only the cosmos, but the very act of observation. In classical physics, the observer is passive. But in quantum mechanics, observation plays an active role determining outcomes, collapsing wave functions, altering probabilities. The observer is not outside the system, they are entangled with it. The more we study quantum entanglement, the more it seems that information is not just stored in things, but in relationships. And those relationships, on large scales, may be what gives rise to space and time themselves. If this is true, then the universe is not built from particles or waves, but from connections, from information. This shift in thinking doesn't make our previous models obsolete, but it reframes them. General relativity still describes gravity beautifully at macroscopic scales. Quantum field theory still works within its energy domain. But these may be approximations, shadows of a deeper framework. And to find that framework, we need to change the way we think. One promising avenue is quantum information theory, the study of how information is processed and transmitted. Physicist Seth Lloyd has proposed that the universe itself is a quantum computer, computing its own evolution through a series of quantum interactions. In this model, particles are qubits, and physical laws are algorithms. The geometry of space is a result of entanglement patterns, and time is simply the flow of computation. This idea aligns with work by Eric Verlinde, who proposed that gravity is not a fundamental force, but an emergent phenomenon, an entropic force, arising from changes in information associated with the positions of material bodies. In this view, what we experience as gravity may be a manifestation of deeper statistical laws. These perspectives are still controversial. They challenge deeply held assumptions, but they are gaining ground, not because they are exotic, but because they offer solutions to problems that our current frameworks cannot resolve. They point the way toward a unified Thoria quantum theory of gravity, a deeper understanding of the Big Bang, and perhaps even a resolution to the cosmic conundrum of dark energy. From a practical standpoint, these shifts in perspective have inspired new approaches in research. Physicists now explore the universe not just as a collection of objects in space, but as a vast network of quantum information. New experiments in quantum computing, quantum communication, and high-energy physics aim to probe these ideas, looking for signs that space and time are not fundamental but emergent. And while we may be far from conclusive proof, the theoretical consistency and explanatory power of these models make them more than speculation. They are the scaffolding of a new paradigm. What does this mean for how we ask questions? It means we must stop assuming that the universe is what it seems, that time flows like a river, that space is a neutral stage, that particles are the smallest pieces of matter. These assumptions are based on perception, not truth. Just as our ancestors once thought Earth was the center of the cosmos, we may be clinging to intuitions that no longer serve us. The universe is under no obligation to conform to our expectations. It may be stranger than we can imagine, but imagination is the very tool that allows us to follow it. That is the role of a shift in perspective, not to replace what we know, but to expand what we are willing to consider. In this sense, science is not a closed book, but a constantly unfolding story, where every answer opens another question. The shift also affects how we communicate science. If we are to explore these ideas meaningfully, we must invite not just physicists, but philosophers, artists, and storytellers to help reframe our understanding. Because we are not just analyzing equations, we are interpreting reality, and that is a task too big for any one discipline. In the coming decades, as our instruments become more sensitive and our models more sophisticated, we may uncover evidence that supports or refutes these alternative views. We may detect patterns in the CMB that reflect a holographic structure. We may discover that black hole information is preserved in a way that reveals the universe's underlying rules. We may find that time, as we experience it, is a macroscopic illusion, like temperature, a statistical consequence of microscopic behavior. Or we may find something entirely unexpected. Whatever we discover, we must be prepared to shift again, because that is the essence of science, and not dogma, but transformation. the willingness to discard beautiful ideas when better ones come along, the courage to look at the universe not as it should be, but as it is. And if that universe is a hologram, a simulation, an emergent construct, or something beyond all categories, so be it. Our task is not to cling to certainty, but to remain open, curious, and bold. So could we be looking at the problem the wrong way? Absolutely. We almost certainly are. But that's not a failure. It's the beginning. Every time we realize our perspective is flawed, we take a step closer to the truth. We become less attached to appearances and more attuned to structure. We move from the surface to the source. And in doing so, we fulfill the deeper purpose of Sciencino, just to describe the world, but to evolve with it, to let go of what was and embrace what might be. Because the universe, in all its mystery, is not static, it is unfolding, and so are we. It began with a pattern subtle, almost ignorable. A slight dip in temperature on the cosmic microwave background map, just a tiny cold spot in the afterglow of the Big Bang. At first, it was dismissed as noise, a fluke in the data. But then, as satellites and ground-based observatories refined their measurements, WMAP Planck, the anomaly persisted. It didn't behave like random interference. It was too coherent, too stable across time and instruments. This cold spot, now known as the CMB cold spot, stood as a riddle, a silent crack in the otherwise smooth fabric of our standard model of cosmology. It was one of many such anomalies, strange alignments, unexpected flows, and unexplained dips in the expected signal from the early universe. But this one refused to fade. It lingered, like a fingerprint left on the surface of the cosmos by something or some outside our current understanding. It was a hint, a nudge, a quiet message that maybe our story was missing a chapter. And it wasn't the only one. In recent years, researchers have uncovered galaxies that shouldn't exist fully formed, massive systems appearing too early in the timeline of the universe, as seen by the James Webb Space Telescope. Their maturity and brightness defied the models. Stars that shouldn't have had time to form had not only formed, they'd aged, collided, and seeded new generations. Even dark matter simulations, when used to explain the formation of these galaxies, fell short. Something was off, something fundamental. And as the cracks in the standard model grew wider, cosmologists and theoretical physicists began to look further afield beyond the confines of a single universe, into the realm of multiverse theories. The multiverse was once the domain of science fiction and fringe speculation. Now it sits near the center of theoretical discourse, supported by developments in inflation theory, string theory, and quantum mechanics. If inflation and exponential expansion of space in the first moments after the Big Bang happened once, why not infinitely? In many models, inflation never completely ends. It simply slows down in regions, creating bubble universes with varying laws of physics. Our universe may be one bubble in an endless foam. Some may contain no stars. Others may have different constants, gravity stronger, atoms unstable, dimensions curled in different ways. It's a landscape, a cosmic archipelago of realities, each shaped by chance and law, expanding forever. This view reframes everything. If the multiverse is real, then our universe is not unique. It is one of countless others, each with its own rules, its own possibilities. The fine-tuning we see the way fundamental constants are so delicately balanced to allow life may not be a miracle or design, but a statistical inevitability. We exist in this universe because it allows beings like us to emerge. In others, no observers arise. This is the anthropic principle writ large, but the multiverse carries disturbing implications. If every possible outcome occurs in some universe, then everything you might do, every decision you might make, has already been made somewhere. Free will becomes a branching tree of infinite versions of you, each unaware of the others. Identity fractures, causality blurs, and worse, verification becomes almost impossible. If we cannot observe other universes, can we call them science? Can we test the theory? Or is it a metaphysical ghost wearing scientific clothes? Some physicists push further still. They look at the patterns in quantum mechanics, the strange duality of particles, the instant communication of entangled states, the observer effect and ask if we're misunderstanding the nature of reality entirely. One interpretation of quantum mechanics is the many worlds interpretation, which suggests that every quantum event splits the universe. At each fork in the zodiac particle's position, spin, or interaction, reality divides. The universe becomes a branching tree of all possible outcomes. In this view, the multiverse is not distant, and disconnected it is intrinsic, woven into the very evolution of quantum states. Every version of you exists. Every possible history plays out. The cosmos is not one timeline, but a quantum braid of infinite paths. And then there's the simulation hypothesis, proposed formally by philosopher Nick Bostrom in 2003. The idea suggests that if it's possible for an advanced civilization to run simulations of consciousness, and if such simulations are easier to create than actual universes, then it follows that simulated minds could vastly outnumber biological ones. Statistically, we are more likely to be inside a simulation than not. It's a bold claim, one that blurs science, philosophy, and digital theory, but the clues are eerie. The mathematical structure of the universe, the fact that particles behave according to equations, that constants remain constant, that reality appears quantized at the smallest levels can be seen as signs of code. Some researchers have even speculated that high-energy cosmic rays appear to hit certain energy ceilings as if encountering computational limits. Others have pointed to the discovery of error-correcting codes embedded in the equations of string theory and echo, perhaps of a deeper substrate. Of course, the simulation hypothesis is controversial. It lacks direct evidence, and yet it resonates with other developments in theoretical physics. If the holographic principle is true, and our universe is a projection of information from a two-dimensional surface, how different is that from a simulation? If consciousness arises from information processing, could it be instantiated in silicon as easily as in neurons? And if we are inside a simulation, who or what created it? Is there a purpose? A watcher? Or are we the emergent byproducts of a self-generating algorithm wandering in digital dreams? This line of questioning isn't just abstract philosophy, it's a shift in how we see everything. It forces us to rethink our assumptions about matter, mind, and meaning. If we are simulated, or even if the universe is structured like a simulation, then the edge of reality is not spatial but logical. The question becomes not, what is out there? But, what are the rules of the system we're in? And this brings us to the most unexpected twist of all. The realization that our quest to understand the cosmos may be as much inward as outward. That the structure of the universe is reflected in the structure of consciousness. That we are not outside observers, but embedded participants, entangled with the cosmos in ways deeper than measurement. The universe is not just a thing we study. It is something we are. In quantum mechanics, the act of observation affects the observed. In cosmology, the act of modeling affects what we prioritize and perceive. Theories are not neutral. They are shaped by our limitations, our tools, and our desires. The discoveries of the last few decades have shown us that our most basic category of space, time, matter, may not be fundamental. That what we call reality is a layered construct, built from deeper, invisible rules. And in that realization lies both humility and wonder. We are not at the center of the cosmos. But we are not irrelevant either. We are the interface consciousness embedded in structure, structure shaped by consciousness. A feedback loop, a question asking itself. The multiverse, the simulation hypothesis, the holographic universe, all these models suggest that what we perceive is not the totality, but the surface, a thin slice of a richer, more complex reality, a shadow cast by a higher dimension, or a narrative written in lines of code. These ideas are not meant to displace science, but to expand it. To remind us that discovery is not just about finding answers, it's about questioning the frame, asking whether the canvas itself might be different than we thought. And so we arrive at a deeper realization, that the cosmos is not merely vast, it is layered, recursive, reflexive. That the greatest mysteries are not always out there, among the stars, but in the nature of awareness itself. The shift from a singular universe to a multiverse, from space as substance to space as code, from reality as objective to reality as emergent, these are not just shifts in theory, they are revolutions of thought. They change how we see ourselves, not as cosmic orphans in an indifferent void, but as expressions of an underlying logic and architecture of possibility. In every model, whether infinite universes or simulated code, there is something precious about this version, this world, this moment. Because no matter how many versions exist, this is the one you are living. These are your questions, your consciousness, your connection to the mystery. And that, in the end, may be the greatest twist of all, that the search for the universe's edge, for its origin, for its meaning, has brought us back to ourselves not in arrogance, but in recognition. That to understand the cosmos is to understand awareness. That to peer into the void is to find a mirror. And that maybe, just maybe, the universe has been trying to tell us this all along, not through words, but through wonder, through the unanswered questions, through the cold spots and anomalies, through the feeling late at night that there is more, always more, not just out there but in here. The horizon of our cosmic understanding has never been closer, and yet paradoxically, never more unreachable. As we've charted galaxies, decoded background radiation, measured gravitational waves, and mapped the deep structure of the universe, each discovery has deepened our knowledge and simultaneously illuminated the vast regions of ignorance still ahead. We've detected thousands of exoplanets, identified the acceleration of cosmic expansion, and unearthed paradoxes in black hole thermodynamics and quantum entanglement. But now, we stand at a turning point in human inquiry, where the questions have become more precise, more urgent, and more profound while our tools, though advanced, are no longer enough. The next frontier will not be crossed by theory alone. It demands a new era of precision, power, and innovation in observation because the universe is not done surprising us, and the biggest revelations still lie in the spaces we cannot yet see. One of the most significant limitations facing cosmology today is the boundary of our observational reach, the so-called cosmic light horizon. The observable universe is bounded by the distance light has been able to travel since the Big Bang, approximately 13.8 billion years. Due to the expansion of space, this corresponds to a sphere with a radius of about 46.5 billion light-years. Beyond that lies the unobservable, galaxies, clusters, and possibly entire cosmic structures that no photon will ever carry to our instruments. This isn't a problem of inadequate technology, it's a structural constraint imposed by the nature of space-time itself. And yet, it is precisely in this unreachable zone that the most tantalizing questions persist. Does the universe curve back on itself? Is it infinite, or simply very, very large? Do physical constants change in different regions of space? These are not academic questions. They shape how we model the birth, evolution, and fate of the universe, and they require imaginative approaches to even begin addressing. Closer to home, there are dozens of unsolved problems we could tackle life. Only our instruments were sharper. Chief among them is the nature of dark matter, the invisible scaffolding holding galaxies together. We know it exists because we can see its gravitational effects. Galaxies rotate too quickly at their edges to be held together by visible matter alone. But no telescope can see dark matter, and no particle accelerator has found the particle responsible. Is it a weakly interacting massive particle, WIMP, an axion, a sterile neutrino? Or is gravity itself incomplete, requiring modification at galactic scales? Current detectors like the Large Underground Xenon LUX experiment are approaching their sensitivity limits without a confirmed detection. Future experiments like the LUX Zeppelin upgrade, the Xenon NT, and the Super Cryogenic Dark Matter Search, Super CDMS, hope to dive deeper, but there's no guarantee. The window may be smaller than we thought, or we may be looking for the wrong kind of signal entirely. Then there's dark energy, the force behind the accelerating expansion of the universe. It accounts for nearly 70% of the energy density of the cosmos, yet remains utterly mysterious. Is it a true cosmological constant? A dynamic field like quintessence? Or is it a sign that general relativity breaks down at large scales? To answer these questions, We need to map cosmic expansion with extreme precision, measuring how it has changed over time and how structure has formed under its influence. This is the goal of next-generation missions like ESA's Euclid satellite and NASA's Nancy Grace Roman Space Telescope. These missions will survey billions of galaxies, probing the geometry of the universe and the behavior of dark energy with unprecedented accuracy. But even these tools may fall short of resolving the nature of dark energy directly. It may require breakthroughs in quantum gravity, in the intersection of particle physics and cosmology, new theory that unites the large with the small. And we are not there yet. Gravitational wave astronomy presents another vast opportunity and a massive challenge. Since LIGO's historic detection in 2015, we've entered a new era in observation, one that listens rather than sees. Gravitational waves can reveal events that light can at merging black holes, neutron-star collisions, perhaps even echoes from the early universe. But current detectors are limited in sensitivity and frequency range. They miss low-frequency waves from supermassive black hole mergers, which are expected to be abundant in the distant universe. The planned Laser Interferometer Space Antenna, LISA, a joint ESA-NASA mission scheduled for the 2030s, aims to address this. With detectors spaced millions of kilometers apart in solar orbit, LISA will be able to capture waves from sources we've never heard before. But it too will face hurdles: data volume, signal confusion, and the need for long-duration stability in the harsh environment of space. Interferometry on such scales demands exquisite engineering, and any noise from solar flares to internal oscillations can corrupt the signal. In addition to technological challenges, theoretical tensions continue to mount. General relativity, for all its elegance, is incompatible with quantum mechanics. The search for a theory of quantum gravity, one that unites the smooth fabric of space-time with the jittery world of particlesis, ongoing. String theory, loop quantum gravity, causal dynamical triangulation siege, offers partial solutions and powerful insights, but none has been conclusively verified. Part of the problem is that many predictions lie beyond current experimental reach. We can't probe the Planck scale, where these effects dominate. We can't peer into the heart of a singularity or recreate the energy densities of the early universe. This is where particle physics meets a wall. The Large Hadron Collider, LHC, our most powerful accelerator, has yet to detect supersymmetric particles or other expected signs of physics beyond the Standard Model. Plans for larger colliders, such as the Future Circular Collider, FCC, or China's Circular Electron Positron Collider, CEPC, are being discussed, but funding, politics, and practicality all pose barriers. Beyond the big questions of dark matter, dark energy, and quantum gravity, there are more subtle but equally profound mysteries. Why is there more matter than antimatter in the universe? This asymmetry is not predicted by the Standard Model in sufficient magnitude. Where are the magnetic monopoles predicted by grand unified theories? Why do fundamental constants like the speed of light, the gravitational constant, or Planck's constantave the values they do? Are they truly constant, or have they changed over cosmic time? And what is the true shape of the universe? Is space flat, or does it wrap around in ways we cannot yet detect? Each of these questions points to the same underlying issue. We need new data, new perspectives, instruments that can see further, deeper, and in more dimensions. Future missions like the Cosmic Origins Space Telescope, COST, and the Habitable Exoplanet Observatory, HABEX, promise to push the boundaries in astrophysics and astrobiology, hunting for biosignatures on Earth-like worlds, and testing the limits of life in the universe. But even these missions are limited by current materials, budgets, and physics. What we truly need is a leap change, as revolutionary as radio astronomy, space telescopes, or quantum mechanics. Perhaps in the form of quantum sensors that can detect gravitational perturbations at planetary scales. Perhaps in orbiting interferometers that can achieve resolutions millions of times greater than Hubble. Perhaps in new ways of analyzing data itself, using artificial intelligence not just to recognize patterns, but to generate hypotheses, to explore theoretical landscapes beyond human intuition. Indeed, the role of AI and machine learning in science is becoming more central. With massive datasets from JWST, LIGO, Gaia, and future missions, the challenge is no longer just observation, it's interpretation. We are entering the era of data-driven discovery, where algorithms will comb through petabytes of information, identify anomalies, simulate universes, and even refine models. But with that comes new dangers: bias, overfitting, mistaking correlation for causation. The more powerful our tools, the more rigorous our methods must be. Science will remain a human endeavor, but it will be increasingly symbiotic, with machines doing what we cannot, and humans guiding the questions machines don't know how to ask. And we must not forget the final challenge: philosophy. Not as a rival to science, but as its silent companion. As our models become more abstract, our theories more counterintuitive, we risk losing the meaning behind the math. What is space if it is emergent from information? What is time if it flows differently depending on the observer? What does it mean to exist in a multiverse? These are not just metaphysical puzzles. They are central to how we interpret data, how we communicate discoveries, and how we make sense of a universe that seems less and less designed for our understanding. Future research must integrate not just disciplines, but perspectives bridging cosmology, quantum theory, computation, and philosophy into a new synthesis of inquiry. So what hurdles remain? All of them. The edge of physics is jagged, not smooth. The problems we face are not incremental, they are foundational. But that is the nature of great transitions. We are at the point in scientific history where the scaffolding is shaking, where assumptions are cracking, where models no longer yield easy answers. And yet, we continue. We build better instruments. We train sharper minds. We dream larger dreams. Because the universe, in all its depth and silence, invites us not to solve it, but to engage with it, to dance with its complexity, to ask, to measure, to imagine. The unanswered questions are not a sign of failure, they are signs of life, of growth, of movement toward understanding. And they tell us this: that the greatest discoveries still lie ahead, not in the equations we've already solved, but in the questions we've barely begun to ask. That the most important tools of the next century will not only be new detectors and larger arrays, but new eyes. Eyes that can see not just further, but differently. Eyes that are willing to look at the familiar and see the strange. Eyes that recognize that the horizon is not a limit, but an invitation. In the vast cathedral of science, where questions echo louder than answers, we find ourselves standing at the edge of knowledge, both thrilled and tormented by what remains unseen. The universe, it turns out, is not easily satisfied with our best models. It resists unification, laughs at linear progress, and presents itself like a mosaic of brilliant fragments waiting to be assembled. And now, after centuries of building those fragments, general relativity, quantum mechanics, particle physics, thermodynamics, we approach a long-awaited confrontation, not between humans and the cosmos, but between the frameworks we've built to understand it. This is the final confrontation of modern physics, the battle to reconcile the grand with the granular, to uncover whether the universe has a boundary, conceptual, spatial, or temporal land, to forge a new era of cosmology built not on broken bridges, but on unified terrain. At the heart of the debate are the two great pillars of modern physics: Einstein's general relativity and quantum mechanics. Relativity describes the smooth, continuous warping of space and time by mass and energy. It governs galaxies, black holes, and the expansion of the universe. Quantum mechanics, by contrast, describes the grainy, probabilistic behavior of particles and forces at the smallest scales. It rules atoms, quarks, photons, and the strange phenomenon of entanglement. Both theories work extraordinarily well within their domains, but when brought together, they collapse into contradiction. Black holes, where massive gravity intersects with the quantum realm, reveal these tensions most dramatically. Near the singularity, space and time themselves break down. The equations of general relativity predict infinite density, while quantum theory insists on uncertainty and granularity. Both cannot be right, or more accurately, both are incomplete. And so the most important project in contemporary physics has become the search for a unified theory of framework that can explain all of nature's forces in one elegant, coherent whole. One of the leading contenders is string theory, which proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings, existing in multiple dimensions beyond the familiar three of space and one of time. In string theory, gravity emerges naturally alongside the other known forces, and the infinities of black holes and the early universe can be tamed by the theory's built-in mathematical structure. It offers a potential bridge between the quantum and the cosmic, but at a cost. It requires the existence of extra dimensions, usually 10 or 11 total, and its landscape of possible solutions is so vast, perhaps 500 different vacua, that it risks becoming unfalsifiable. Despite decades of work, string theory has yet to make a testable prediction confirmed by experiment. Still, it remains a powerful conceptual framework, influencing ideas from the AD-CFT correspondence, a holographic duality that connects a gravitational theory in a higher dimensional space to a quantum field theory on a lower dimensional boundary, to the nature-influencing field theory in a higher dimensional boundary of entanglement and space-time emergence. An alternative approach is loop quantum gravity, LQG, which takes a more minimalist path. LQG starts from the principles of general relativity and attempts to quantize space itself. In this theory, space is not continuous, but composed of discrete chunks or loops connected in a vast network like atoms of space. Time, too, may be quantized, emerging from the relations between spatial structures. Loop quantum gravity avoids the need for extra dimensions and has produced models where singularities are avoided, for example, where a collapsing black hole rebounds into a new region of space-time, giving rise to a bounce rather than a point of infinite density. But LQG has its own challenges, particularly in connecting its discrete structure to the smooth behavior of large-scale gravity and in reproducing standard particle physics. While less grandiose than string theory, it offers a compelling vision of spacetime as a fundamentally quantum entity. Still others pursue emergent gravity theories, which suggest that gravity is not fundamental at all, but a statistical effect of microscopic degrees of freedom, much like pressure or temperature emerge from atomic motion. Eric Verlinde's entropic gravity, for instance, proposes that gravity arises from changes in the amount of information encoded in the positions of matter. These theories are tantalizing because they offer new ways to interpret dark matter and dark energy not as particles or fields, but as emergent properties of spacetime. But again, they are controversial, and their predictions remain difficult to test. These competing theories form the front lines of the final confrontation, a battle not of conflict, but of convergence, where decades of work in black hole physics, cosmology, and particle theory are brought together in search of deeper truths. Central to this is the question: will we ever find a true boundary? Not just a limit to the observable universe, but a fundamental boundary in nature, something that defines the edge of what exists, or what can be known. In the past, we thought the Earth was bounded by oceans. Then we thought the galaxy was the entire cosmos. Now, we speak of the cosmic horizon, the limit of what light has had time to reach us from. But beyond this lies the mystery of the global structure of the universe. Is it infinite or closed? Does it repeat? Is it embedded in a higher dimensional space? Or is our whole universe merely one region of a vast multiverse, with other pocket universes separated by inflating walls of spacetime? Inflation theory itself, now a well-supported model of the early universe, predicts that inflation never stops, that it creates a multitude of bubble universes. This eternal inflation model gives rise to the multiverse idea, a cosmic ensemble where each universe might have different physical laws and constants. If true, this not only pushes the boundary of our universe beyond observation, but forces us to reconsider what a law of nature even means. Are the laws we observe merely local rules, selected by chance or by anthropic necessity? Are we typical observers or cosmic flukes? And if the multiverse is real, how could we ever confirm it? These are not just speculative questions. They are now central debates in cosmology, influencing how we interpret data and frame theories. This search for boundaries, whether spatial, conceptual, or epistemological, has also led us into the frontier of quantum information. Increasingly, physicists are coming to believe that space-time itself may emerge from quantum entanglement, the mysterious link between particles that allows them to affect each other instantly, even across vast distances. In this view, geometry arises from networks of entangled information. Black hole entropy, the holographic principle, and the structure of the vacuum all point toward a universe built from relationships, not objects. The boundary may not be a surface in space, but a threshold in information, a limit to how much can be known, or how finely space-time can be sliced. This perspective unites relativity and quantum theory, not by merging equations, but by reframing the problem. Not what is space, but what is information. As these theories compete, challenge, and inform one another, a new vision of the future of cosmology emerges soon that is interdisciplinary, data-driven, and deeply philosophical. Technological advancement remains key. The upcoming LISA mission will detect gravitational waves from cosmic-scale events. The Roman telescope will map dark energy through weak lensing and supernova surveys. Future projects, like quantum gravity observatories, might even probe Planck-scale physics indirectly through subtle correlations in the cosmic microwave background or fluctuations in space-time noise. Artificial intelligence will also play a growing role not only in analyzing data, but in exploring theory. Machine learning can simulate universes, explore parameter spaces, and even help derive mathematical relationships that humans might overlook. And as data from JWST, Euclid, and next-gen detectors flood in, we will need new paradigms to integrate observation and theory to move beyond the current schism between elegant but untestable models and observable but limited phenomena. So what is the ultimate fate of this confrontation? Will we find a final theory? A theory of everything that resolves all contradictions? Perhaps, but perhaps not. It's possible that reality itself resists closure, that there is no single equation, no final boundary, only a hierarchy of layers, each revealing a deeper level of structure and meaning. If so, the future of cosmology is not about conquering mystery, but about learning to live with it. To embrace a universe that is not a puzzle to be solved, but a symphony to be heard, where each new theory is a movement and each discovery a note. And if we never find the true edge, if space goes on forever, or time has no beginning, or if we are inside a simulation with no access to the source code, then we will still have done something extraordinary. We will have learned how to ask questions that expand not just our knowledge, but our very capacity for awe. We will have joined the cosmos not by mastering it, but by becoming aware within it. That, perhaps, is the real final unification not of gravity and quantum mechanics, but of mind and universe, question and silence, science and meaning. This is the final confrontation. Not a war between theories, but a convergence of frontiers. And whether we find the edge, the center, or neither, one thing is certain: we are not done. The cosmos is not done with us. And the next chapter is already being written. In the grand theater of the cosmos, amid the spiraling galaxies, the dark silent voids, and the flickering afterglow of the Big Bang, humanity appears as a fleeting phenomenon, a species born of stardust, momentarily conscious, gazing up into the black sky, asking questions so bold they echo across epochs. We are young, fragile, bound to a small planet, but within us burns something ancient and powerful: the need to understand. This instinct, this relentless curiosity, has driven us from the safety of myth to the discipline of science, from imagining gods in the stars to mapping those stars with equations, from believing Earth was the center of all creation to knowing it is one small island in an infinite sea. And yet, the more we learn, the more we realize how little we know. Every discovery pushes the boundary of ignorance outward. Every answer births a deeper question. And in that endless dance between knowledge and mystery, we discover not just the workings of the universe, but something essential about ourselves. The deeper meaning of exploring the unknown is not just intellectual, it is moral, spiritual, and existential. We are the only known species to question its place in the cosmos. The only life form, as far as we know, to ask not only how things work, but why they exist at all. That capacity is not a byproduct of intelligence, it is the signature of it. We explore not because we need to, but because we must. Because to stop wondering is to stop being fully human. In the cold equations of cosmology, the sterile void of intergalactic space, and the silent signals of gravitational waves, we find something unexpectedly profound, a reflection of our inner need to connect, to belong, to matter. The act of exploration becomes a mirror. It shows us what kind of beings we are, and what kind we might become. Curiosity, then, is not frivolous. It is not a luxury. It is the engine of progress, the spark behind every leap forward. It led us to fire, to language, to the stars. It built telescopes, launched satellites, split atoms, decoded genomes. It pushed Galileo to turn a telescope skyward, Einstein to rethink time, and modern physicists to chase particles that flicker into existence and vanish before they can be touched. Curiosity has always been an act of courage, a refusal to accept easy answers, a rebellion against complacency. It dares us to confront the unknown not with fear, but with fascination. And this drive is especially important in a world that often rewards certainty, control, and fast results. Science, true science, requires the opposite. It requires humility. It requires patience. It requires the ability to live inside a question for years, even decades, without resolution. And it demands that we accept failure, revision, and uncertainty, not as obstacles, but as signs of growth. The balance between knowledge and mystery is delicate and often misunderstood. We do not seek to eliminate mystery. We seek to illuminate it. The universe is not a puzzle to be solved, but a field of questions in bloom. As we learn more about dark matter, black holes, quantum entanglement, cosmic inflation, we are not diminishing the wonder of the universe. We are enhancing it. The more we understand, the deeper the mystery becomes. The more precise our measurements, the more astonishing the patterns they reveal. This is the paradox of cosmic exploration. Knowledge does not replace mystery, it deepens it. And in that deepening, we find our place not as masters of nature, but as participants in something unimaginably vast. This understanding can shape how we live. It can guide how we treat each other and how we care for our planet. When we see Earth from space, a fragile blue dot suspended in darkness, we are reminded that borders are illusions, that divisions are arbitrary, that our fate is shared. We are not many tribes away or one species. The cosmic perspective humbles us, but it also dignifies us. It shows us that life is rare, precious, and delicate. That civilization is a thin layer atop an ocean of uncertainty. That we must cherish what we have and not, just because it is ours, but because it is part of a story billions of years in the making. Exploring the cosmos teaches us more than physics. It teaches us ethics. It teaches us to ask what kind of legacy we want to leave. Do we want to be remembered as conquerors of nature or stewards of a living world? Do we want our science to serve war or wonder? Do we seek knowledge to dominate or to understand? These are not scientific questions. They are human questions. And they matter more than ever in a world where technological power has outpaced moral wisdom. The same rockets that send probes to Mars can carry weapons of mass destruction. The same computers that simulate universes can be used to manipulate truth. The same knowledge that uncovers the secrets of DNA can be used to heal or to harm. We must choose. The cosmos offers perspective. It teaches us scale. Our lives, our empires, our dramasol are brief flashes against a backdrop of stars that have burned for billions of years. And yet, that does not make our lives meaningless. Quite the opposite. It makes them urgent. Every second is a miracle. Every life, a rare occurrence in a universe mostly hostile to life. And every act of kindness, of curiosity, of courage, these are not small. They are how meaning is made in a world that offers none by default. Science does not tell us why to live, but it shows us that life is rare, and that rarity makes it sacred. We have learned that we are made of star stuff, that the atoms in our bodies were forged in the hearts of ancient stars, that we are, quite literally, the universe becoming aware of itself. This is not poetic metaphor, it is physical fact, and it carries a moral implication. If we are the voice of the cosmos, then what we say matters. If we are its eyes, then what we see matters. If we are its memory, then how we live and what we choose to remember matters. We are not insignificant. We are improbable. And improbability is the foundation of beauty. As we continue to explore, to launch missions, to analyze data, to build theories, let us remember this, that science is not cold. It is not detached. It is an act of love for truth, for beauty, for the mystery that surrounds us. It is how we honor our place in the story of the universe, not by clinging to certainty, but by embracing wonder, not by seeking dominion, but by listening carefully to what the cosmos is trying to tell us. The stars do not speak in words, but they have a language. They speak in light, in gravity, in motion, in entropy, and we, alone among the animals, have learned to listen. The moral takeaway of cosmic exploration is simple, but profound. We are small, but we can be great. We are temporary, but we can build things that endure. We are alone for now, but we can choose solidarity over division. The universe does not need us, but we need each other. And we need the dream of discovery to remind us who we are and who we might become. Let us then be worthy of that dream. Let us use our knowledge not to build walls, but bridges. Let us teach our children not just what the stars are made of, but how to wonder at them. Let us fund science not just for its utility, but for its capacity to elevate the human spirit. Let us tell stories of the cosmos not just in textbooks, but in songs and paintings and conversations under the night sky. Let us become a civilization that values wisdom over wealth, awe over arrogance, empathy over exploitation. Because the universe is vast, but so is the human heart, and the journey has only just begun. After thousands of years of wondering, observing, testing, failing, and trying again, we have reached a moment in history where the mysteries of the universe are no longer entirely beyond our grasp. We've seen the first light of creation through the cosmic microwave background, mapped the large-scale structure of the cosmos, confirmed the existence of black holes and gravitational waves, and inferred the existence of invisible entities like dark matter and dark energy. We've built machines that capture the flicker of ancient galaxies and algorithms that model quantum particles beyond our senses. And yet, in spite of all these revelations, or perhaps because of them, we find ourselves face to face with a deeper realization. The more we uncover, the more infinite the mystery becomes. The edge of knowledge does not shrink. With discovery, it grows. And with that growth comes a question older than science itself. Should we strive for a final answer, or accept the mystery as an eternal companion? There is a temptation, a very human one, to close the loop, to end the story with clarity, to find the theory that explains everything, to arrive at a model so complete and comprehensive that it leaves no question untouched. That is the promise of a theory of everything. A single elegant framework that unites quantum mechanics and general relativity, that explains time and space, energy and matter, consciousness and entropy, beginnings and endings. And such a theory may yet emerge. The quest for it drives many of the most brilliant minds on Earth. But even if such a theory were found, would that really be the end? Or would it simply shift the nature of our questions? History teaches us that every final answer has eventually unraveled into new mysteries. Newton's laws seemed unshakable until relativity revealed their limits. Classical physics collapsed under the weight of the quantum world. The Big Bang answered one question: where did the universe come from? Only to raise 1,000 more. Every breakthrough deepens our awareness not of certainty, but of complexity. It is not that we cannot find answers. It's that each answer reveals how much more remains to be asked. And so perhaps the most honest and most profound conclusion is an open one, not because we are incapable of knowing, but because the act of not knowing is itself meaningful. The mystery invites participation. It stokes the imagination. It demands humility. And in a world that often pretends to be certain about everything from politics to philosophy to science, there is something deeply powerful about saying, "We don't know, not yet, maybe never." Leaving questions unanswered is not a failure of science. It is the fuel of science. Questions are the engine of progress, the gateway to wonder, the compass for exploration. The value of an open-ended mystery is that it sustains the conversation between humanity and the cosmos. It keeps our thinking flexible, our curiosity alive, our sense of scale intact. It reminds us that reality is not obliged to conform to our expectations, and that the universe, as Richard Feynman once said, is not only stranger than we imagine, it is stranger than we can imagine. And so, as we draw together the threads of this journey from the edge of the observable universe to the frontier of quantum theory, from gravitational waves to the multiverse, from simulation hypotheses to holographic space, we must recognize that these ideas do not provide closure. They provide permission. Permission to imagine that there is more. That the structure of space and time is just one layer of reality. That the laws of physics might themselves evolve. That consciousness might be entangled with the fabric of the cosmos in ways we have yet to understand. That the map we are drawing is not a wall, but a window. Among the biggest takeaways from our exploration is the recognition that we are not outside observers. We are not separate from the universe. We are made of it. Our atoms were forged in stars, our minds shaped by evolution, our instruments constructed from matter that once roamed the galaxy. When we ask about the universe, we are asking about ourselves. The quest for the edge of the cosmos is inseparable from the quest for meaning, for purpose, for understanding what it means to be in a universe so vast, so ancient, so unthinkably rich. We have learned that time is not absolute, that space can stretch, that matter and energy are two sides of the same coin. We have discovered that most of the universe is invisible, that the forces holding galaxies together are still not fully known. We have realized that black holes can evaporate, that information cannot be destroyed, that entanglement might be the key to understanding not just particles, but the structure of space-time itself. These are not footnotes in scientific history. They are invitations to expand our definitions of what is real. Most importantly, we've come to understand that the universe does not owe us simplicity. It is not required to be understandable. And yet, somehow, it is at least partially, provisionally, enough for us to survive, to predict, to imagine, to build, to dream. That is itself a kind of miracle. That we can make sense of any of it at all. And that miracle deepens, not dissolves, when we accept the open-ended nature of the journey. The future of cosmology will not be defined by finality, but by frontier. There will be new questions we haven't yet imagined, new tools that see deeper, measure more precisely, simulate more completely. There will be new paradoxes, new theories, new collisions between data and belief. And with each, we will move not closer to an ending, but deeper into participation, into awareness, into awe. So what is our final thought on the infinite possibilities of space? It is this, that the universe is not a problem to be solved, but a presence to be experienced, that its value lies not just in its scale, but in its story, that by exploring it, we also explore the most noble and vulnerable aspects of what it means to be human, our hunger for truth, our longing for connection, our willingness to ask questions we cannot yet answer. Should the mystery remain open-ended? Yes, because an open question is not a void, it is a horizon.